Good morning. I'm Phil Sykes. I work in Google's data center network operations team in Dublin, and I'm here to give you a potted history of the, or potted secret history of the 10 years of Google's data center networking. And this is a beautiful picture of our servers and switches in Council Bluffs in Iowa. I warn you, there are no more pretty pictures, and to Remco's note, there may be graphs that go up and to the right somewhere in this slide deck. It takes a village to build your own data center network, and here are the villagers. I'm not on there. I joined in 2011, some way through this project, but I've turned down some generations of this stuff, and I've turned up other generations of it. So most of this talk is about design decisions that we made when we were building these data center networks. And to understand why we made some of those design decisions, it might be helpful to understand what it is we do with our data centers and why it's a bit strange compared to what other people do with their data centers. There's an awesome book that's a free PDF now, The Data Center, or The Data Center as Machine by Urs Holzler, that I recommend for lots of detail on this. But for the potted version of it, this is scale-out application architectures. And this means that the jobs, rather than being run on a few servers, are run on many servers all the way across the data center. And they talk to all the other servers in the data center to do computation. And when they want to reference big data sets, like, for instance, a copy of the internet, that's all stored on disks that are attached to each server. So there isn't a storage network here. As you can imagine, a bunch of machines getting bits of a copy of the internet from each other is pretty data intensive. So the kind of 2004 era data center world looked a bit like this. Pretty quick within a rack, but across the whole of a data center, pretty terrible if you're trying to do things like that. So application owners either had two choices: put up with really terrible performance, or care very deeply about exactly where your jobs are scheduled next to each other, and strand a whole load of resources because we can use the CPUs here to talk to the disks here, but that's all. Those are the only people who can use the disks. So what we'd like is the illusion of the perfect network, infinite free low latency bandwidth across a whole data center. But the important bit of that is flat bandwidth. And that's not something we could build with 2004 era technology, but it was something that we really, really wanted to build, not least to get the application developers out of the business of caring deeply about what the network looked like and trying to optimize for it before they were complaining bitterly. So, we went to talk to vendors. Vendors presented their current TIN and their current roadmaps, and it was pretty clear from those conversations that nobody else had this problem. The kind of scales that we were talking about in 2004 with the big vendors were not the scales other customers were talking to them about. So they had no plans. But you could put their boxes together to scale up. It would just be tremendously expensive, and they were very willing to help us, but we were less willing to pay. But even if we were willing to pay, none of their stuff really looked like it was going to scale as we thought our network was going to need to scale. So both of those two things were bad. The third thing was that we had a whole bunch of experience running thousands of switches by SSHing into them and telling them to do things when you wanted to make changes. And that's actually pretty painful. It's got a bit easier in later years, but back then it was pretty terrible. But there's an aha moment signaled by the light bulb there. And this is both how we were able to do this, but it's also why a whole bunch of this talk will leave people going, this isn't my use case. This isn't most people in the world's use case. And I apologize for that. It really isn't. We build our own servers. We run our own custom OS on those servers. We build all our own applications. There are no third-party applications running in the Google data center. So we really control the horizontal and the vertical. So if I need to make a change to how servers do something or how applications do something so that I can build a cheaper network, I can do that. And that makes for interesting things, but obviously makes for challenges that other people or don't have. So I hope, nevertheless, the kind of 10-year secret history is interesting and there are some things you can take away from it. So there were kind of three pillars in the design, and we're tremendously smug these days because these three pillars have seen much wider general adoption in the last few years. So back at that point, the merchant silicon industry, the idea that a chip manufacturer might make Ethernet switching chips to sell to other people who would make switches out of them was just launching. And the use case for that stuff was really just low-cost Ethernet switches. But that suited us because they were cheap. The second pillar is clause topologies, and that may be the most controversial thing I say in this talk, that I think his name is pronounced clause. So there's a whole bunch of stuff on the internet about how these topologies work and how you scale them up, and I'm not going to cover any of it. The key abstraction is that you can build out to almost any scale you want, provided you're willing to pay the cost of an exponentially increasing number of links and nodes in your data center. So really, without that first one of cheap chips, we don't get to the second one of building out arbitrarily large data centers. So those two are really important together. And at this point, we'd had a fair bit of experience in building data center scale storage management solutions and data center scale job management solutions. So we were really pretty comfortable with centralized control and centralized management. So we decided whatever we built would just be managed centrally, and we would throw out the existing kind of, this is an individual box, it has an individual personality, that was how you manage network devices at that point. So we're building our own hardware. What are we going to run on it? And again, we have the option, we can go out and license the OSPF and BGP stack from somebody who makes that and will sell you the source code for use in your devices if you want. You can also license a Cisco-like CLI from somebody if you don't like your operators very much. But this had a whole bunch of limitations. Clause leads us to really a lot of paths between stages and an awful lot of paths between two servers. So what you need is something that can understand multipath forwarding in great detail. So these days, there's actually a bunch of stuff that can do that. BGP multipath is very well established. Trill and shortest path bridging are both capable of dealing with this sort of stuff. But in 2004, there wasn't. And a lot of this stuff is actually based around building large flat layer 2 domains. Thanks, VMware. The idea of running large layer 2 domains frankly scares us, and frankly should scare anybody with thousands of switches in their data center. So the idea of running layer 3 everywhere was what we wanted, and that was something we just couldn't get. So we're going to build our own software as well. So there are a whole bunch of challenges in coming up with a bright idea and turning it into something that your application owners will actually use in a data center. These slides are mostly distilled from a SIG-COM paper, also called Jupyter Rising, and I'm going to skip through a whole bunch of these, but if you are interested, the SIG-COM paper is a relatively dry but interesting read at a lot greater depth than this. So here's a graph, and on the x-axis you have the year, and on the y-axis is the bisectional bandwidth of the data center. Bisectional bandwidth is, summarized as if I chop the data center in half down all the machines, how much bandwidth can they talk to each other with? So it's a bit more complicated than that, but for this we'll say it's that. So here's 2004. Here's what we're deploying in some great numbers, even back then. So this is the biggest router money can buy in 2004, pretty much. 512 top-of-rack switches, each with 4 1-gig uplinks. So the bisectional bandwidth there is 2 terabits a second. And we can't buy anything bigger, or we can, but we don't want to because it's too expensive. But we need to buy something bigger. And yes, here's the up and to the right graph. So this is 7 years-ish. This is 50x of traffic. And there are a whole bunch of reasons for this. The data sets we work on, the copy of the internet that we build the index from is getting bigger. The applications that we're doing are also getting more demanding, and we're doing interesting new things we couldn't do. But at an infrastructure scale, Moore's law is running along. So you have lots more CPUs with lots more cores on them that are much better able to fill up the network. And also the big one, actually, that changes the slope of this graph towards the end is flash storage. So since we're running deaggregated storage, flash is just infinitely better, almost, at filling up the network than reading off a bit of spinning rust is. Building a data center to support flash is actually one of the big challenges of recent years. So here's the topology, and you may have also heard this called leaf spine. I think most of the reference designs just have 2 layers of switches. This isn't necessarily just 2 layers, it depends on the generation of our technology. But this topology with some leaves down the bottom, some aggregation blocks that TORs connect to, and some spines at the top that all of the aggregation blocks connect to, hasn't changed. And that's really because our use case hasn't changed. We're all about providing the illusion that it is just a single large top-of-rack switch with all of the servers connected to it, to the application teams. So what has changed is the sizes of the chips. Yeah, they've gradually grown more powerful. And what's also changed is the port count on those chips, the radix of those chips. And that's gone both up and down. And that leads to a different number of stages to achieve the same goal. But yeah, this design works very well if your traffic can be approximated by every server talks equally to every other server, which sounds a bit fanciful, but actually at the aggregate of a data center scale for us, that's a pretty good assumption. So this topology really hasn't changed for us across the 10 years of building stuff. So, 2006, skipping over Firehose 1.0, which never made it to production for a variety of terrifying reasons. Merchant silicon, state-of-the-art at this point, is an 8-port, 10 gig chip. The connector on the front of those things that we built into a switch with 6 line cards, you probably won't recognize because it's an InfiniBand 4X connector. And we ran copper CX4 cables. And I hope you don't know what those are because they're awful to work with. They have a range limitation of about 14 meters, and if you've heard of the Cat5 of 9 tails, that would only scare people. Something made of these cables would kill people. So nobody actually deploying these in data centers loved them very much, but we were able to build a network with 10 terabits of bisection bandwidth in it. Other interesting features that come in and out of what we do, that chassis there, the line cards aren't connected to each other. All of the connections happen out of the front, which confuses people very greatly when they first see it. The other thing is that they don't run a management protocol between them. There's a copper Ethernet switch over on the, or copper Ethernet port, and that runs off to a separate control plane network that we built on vendor, standard vendor 1 gig E switches because we didn't really feel like running our control plane for our unreliable technology on our unreliable technology. So those 2 things come back again and again, that we have an out-of-band control plane network and that we have a whole bunch of stages that interconnect to each other. So getting this into production and convincing people that this is a good idea to go put in the network was difficult. So we ended up with a compromise of building it as a bag on the side. So every top-of-rack switch still has a nice reliable connection to its original network design. But we also have this 10x larger bag on the side that they can use to communicate to each other, which is where all the traffic's going. 90+% of the traffic, 99+% of the traffic these days stays within a data center. Not much of it wants to leave for most of our applications. So this has the great property that if it breaks, you can turn it off. So that's a great upside. The downside was pretty much everything else, and the operations team were really glad to see the back of this relatively recently, and every all hands of infrastructure we would send one brave person to ask, please can we turn this stuff off this year, and the finance people would shuffle their feet and go, yeah, we'd still like it to be running. So that's 2006 10T. Fast forward to 2008 and the state-of-the-art merchant silicon is now 16 ports of 10 gig. So we've built it into what looks a lot like a standard chassis switch. And we've done that by putting 3 chips onto a line card and then put 8 line cards in a box. So we have, I think, 128 ports coming out of it. And learning our lesson about the terribleness of CX4 copper cables, however price attractive they are, this is fiber everywhere with 10 gig SFP pluses. And this led, the scale at which we deployed this globally, led a clever analyst to add up all of the shipments of 10 gig SFPs and realized that there was a big hole in the forecast that he couldn't explain, and to suggest that Google might be building its own networking equipment and buying its own SFPs for it. Our official response to that is still no comment. We scaled up to 82 terabits a second here, so it's about another 10x. And this was deployed globally and is running still today, and I still have some love in my heart for this, not like Firehose. Fast forward another year, and two things happened. One is we have a 24-port 10 gig E merchant silicon switch, which is great because we can build a bigger network. The other thing is that 10 gig E uplinks on servers are becoming cost effective, and we're starting to deploy them. So that's bad from a data center perspective because we now have 10x the demand at the bottom. So we very rapidly built out a new set of applications, which we've started naming after planets at this point. So the Saturn chassis replaces Watchtower. This is a 288 10-port switch. And it's worth remembering this is still the era of the Cisco SUP 720. The SUP 2T is still a couple of years away. So this is way bigger than anything we could buy on the open market at this point. But there's also that 10 gig E top of rack switch, that the Pluto. Many people might have seen that turned up at somebody's house, misdelivered at one point. We had to dispatch the black helicopters with friendly Google people with free T-shirts in and politely ask for it back. Somehow that didn't make as much press as we thought it might. But yeah, that was one of those, and we've been a bit more careful about who we use to ship them since. So this chassis actually is still running today in a number of applications. So we extended that illusion of a single flat domain of bandwidth out of a single data center building into a campus of data centers. So there's a thing called a free dome that all of these things connect to so that they can talk to each other. And that allows us to scale even bigger, so we can have a large area, acres full of data centers that talk to each other. Both for trying to do exceptionally large computing, but also for resiliency reasons. If you've got some kind of replica write system, you might want some of your replicas to be outside the building. And if you're trying to build a replica of the internet, that might be a relatively big number. So we deployed these as well in preference to the previous thing, which was kind of interconnecting them with big vendor routers, which was pretty expensive. And then around this time, we started to think about our private WAN, because we need to send things like copies of the internet across to the other side of the world. And trying to do that and paying vendor prices for WAN router ports is pretty terrible. So a bunch of you may have seen that we talked publicly a couple of years ago about B4, which is our backbone network that runs in parallel to our vendor backbone network, that carries all of the kind of bulk traffic that can survive not being quite as available as something you build on a vendor network. So yeah, this chassis has seen use in a whole bunch of different places. And yeah, this takes us up to 270, and then we skip a while because actually that's been pretty good for us. But then the advent of flash storage and the advent of 40G mean that we're running out of runway. So 3 years later comes Jupiter, hence the Jupiter Rising name of this presentation. So that's a really big number over on the other side. So here's Jupiter. State-of-the-art merchant silicon is 16 by 40 gigs in 2012. So we go back to building that into small chassis with a 3U chassis called a Centauri with four of those chips in it. Doesn't have a backplane again. Everything connects out of the front of the chassis. And we use that chassis for everything from top of the rack switches all the way up and down the network. And there's two really good reasons for that. One is that if you use the same thing for everything, sparing and manufacturing and that sort of thing becomes a lot easier. The other is that if you build everything out of really small building blocks, the maintenance of those building blocks becomes a lot easier. If a big chassis switch fails, that's kind of a bad day for everybody who is connected to it. If one of these fails, great, we'll just have somebody repair it. And that, from an operations perspective, that makes things a lot better for me because I can actually turn up, I can actually take one of these down for an upgrade, and nobody really notices. I don't have to declare a maintenance window and sit at a very tedious change control board, which makes me happy. So here's the actual tin. There's 32 of these in a couple of racks. There's 20T of bandwidth up to the spine, and there's 20T of bandwidth down to the top of rack switches. And we've also deployed OpenFlow here. So we've taken the control plane and moved it out onto an x86 server that's sitting on that control plane network. And that does all of the heavy lifting of root computations. And the little CPUs on these guys are really just sending keep alive messages to each other and responding to controls from elsewhere. So there's 10 years of history, up to 1.3 petabits a second. I fear I may not have all the time I wanted to discuss all of this, but we'll skip through some of it. One big problem we had is that these cheap Ethernet switches have very small buffers because they were supposed to be LAN switches. But again, we control horizontal and vertical, so if we want to deal with congestion, we can actually make ECN work. Because we have a tiny round trip time, stuff can actually respond to congestion really quickly. And we can have the hosts realize that there are many parallel paths, and if they're experiencing congestion on one path, maybe they should change some entropy a bit and get hashed across a different path and see if that works better for them. And this HA thing is, you've heard of perhaps of the analogy of servers as pets versus servers as cattle. This is network switches as cattle rather than pets. So we don't build massive redundancy, redundant everything into the switches. We do build redundant power, and we don't build things like in-service software upgrade, which never works. We just implement what we need, and if something's misbehaving, we tell everybody not to use it, and we turn it off and on again until it stops misbehaving. It's not all been Guinness and Skittles, so we've had a whole bunch of outages across the years. The three broad categories here, stuff breaks at scale, and those little embedded CPUs, which we were trying to ignore, came back to kill us. So we have the centralized control reacting to things that happen and telling the switches, and we have the switches sending data plane liveness messages to each other. Then we rebooted 32 of the top-of-rack switches, and it never converged. They were so busy telling each other that they were rebooting and receiving updates that they forgot to send heartbeats to each other, so everybody thought everything was churning. So yeah, we had to turn it all off again and on again slowly to fix it. So we realized we had a scale testing problem, and one of the nice things about developing a lot of the control plane as software is that it's very amenable to the same kind of unit and integration test approaches that you use for real software. So we then developed a whole bunch of virtualized test beds that mimic having a couple of thousand switches and mimic them misbehaving. So that was great for us. Yeah, we can now test at the biggest data center we want to deploy scale and make sure the control plane works without having to build out many megawatts of test equipment. Second bit, if you have an out-of-band control plane, your network cannot really be more reliable than your control plane network. And as it got newer, or as the hardware got older, we encountered a whole bunch of failure modes that we just totally ignored, because there's lots of things about a data center that you don't need centralized control or decentralized control for. You don't think it's ever going to partition. You don't think a bunch of stuff is ever going to happen. But as the hardware gets older, yes, it will. And really, you need to pay as much attention to this network as you did to your data plane network. And we learned that lesson late and painfully. Finally, component misconfigurations, which was changed from human error on an earlier version of this slide to be less unkind to people like me. So we have a whole bunch of upgrade automation, same kind of problems as any other upgrade automation, sequencing and checking. But also things like tools hardening when humans override it. If I tell you to reboot switches and I don't give you a list of switches, assuming that I want to reboot all the switches in the data center is a really poor assumption, but perfectly valid for a bunch of people who build tools to run in a test lab. So yeah, thankfully Google has a blameless post-mortem culture, of which I am living proof because I still work there. So there we go. We got to a flat bandwidth profile mostly across all servers. Our application developers love us and can write stuff without thinking about the network in most cases. And we've scaled up to a petabit scale in under a decade. There's a really interesting presentation on generating enough traffic to test that, which sadly I won't have time to give you. And as a bonus, we give, we have a campus aggregation and WAN network that use these same principles and the same cheap hardware. And as a double bonus, everybody in the industry seems to be going with kind of white box switching, big clos networks and that kind of thing for data centers. So amongst our other properties, we are also very smug. So that's pretty much it. I can take some questions. My one caveat is that although it appears Google is being less secretive about all of this kind of thing, it is only being selectively less secretive. So I apologize in advance if I can't answer your question. Okay, thanks very much.
Hi, I'm Nick Hart from Lancaster University, and thank you for an illuminating presentation. My colleague's been talking about whether you use OpenFlow. in your network for a long while, and we just guess. So now I can say yes. You said it's a rather unusual use case, and I'm wondering whether that's really true, because if you're looking at other big cloud deployments, you know, say AWS, if you're doing an overlay network, then actually it seems to me what you've just built is the underlay. And it's not necessarily that different from a lot of other cases, or am I being too simple there?
No, I'd say these days, actually, I'd expect all of my web-scale colleagues to deploy exactly the same stuff. I'm not sure where between 2004, when we started doing it, and now that point was, but I don't think this is a new game anymore. Hence, we're talking about it.
Dave Reader. Something you said in that interested me a little bit, is you said two things that don't automatically sit well together. One is that you don't want a big layer 2 network for obvious reasons, so you want it all to be layer 3. And the other is that you want this to appear that this is every machine in the data center is connected to one big switch. So in my head I'm wondering, is this a separate layer 3 network for every host, or is it carved up some other way? Can you shed some light there?
It's actually a subnet per top of rack switch. Application developers who relied on the property of being able to reach some other hosts at layer 2 without talking IP, that's basically never worked in our network. So they haven't developed that bad habit.
Okay. And just a trivial second thing, how do you choose the naming for these projects?
They're all named after planets, and effectively the lead architect picks the next bit of the solar system we haven't explored. Okay, thanks.
Thank you very much, Phil.